All right, so now we're going to get into another reaction here, catalytic hydrogenation. And by hydrogenation, you're going to see that we're adding hydrogen to both of those vinyl carbons. So hydrogenation is adding hydrogen to one and the other. This actually uses hydrogen gas. Those are the source of those two hydrogens. And it's called catalytic hydrogenation because they require a catalyst. In this case, they're using metal catalysts. So it's like a surface catalyst. We'll see a few different ones. Platinum, palladium, nickel are the three most common ones. Okay, but these are going to create alkanes, right? We're going to taking our alkene, and to each of these vinyl positions, all we're doing is adding a hydrogen, adding a hydrogen. Well, in terms of how we draw our bond line structures, hydrogens are implied. So it's kind of what it looks like is we've just taken this alkene and erased that double bond there. All right, so we're forming alkanes through catalytic hydrogenation. Important because, and we'll see why this is, it has to do with the fact that these are surface catalyzed reactions, that these are syn additions. So both hydrogens are going to be added to the same side. So what would that look like here for this compound? Again, both of these hydrogens, in this case, both of them were being added below. Or I could have my other stereoisomer, which is the mirror image, implying that both of the hydrogens were added from above, right? But this is a syn addition. Both of those hydrogens are going to be added to the same side of that double bond. So catalysts, what is a catalyst doing for us? Catalysts just speed up reactions by lowering that activation energy barrier. In this case, these reactions don't actually occur without the presence of a catalyst because the activation energy is just too high. Our catalyst is, again, a surface catalyst. So it's literally a metal that you've treated with hydrogen gas. The hydrogens actually stick to that surface. And then when your alkene comes and approaches, it'll pick up those hydrogens from the surface. But notice that's why it's a syn addition, because both of those hydrogens are kind of just like sticking up on this metal surface, and that double bond comes. And so both of those hydrogens are added to the same side. One of the things you got to be careful with that wasn't a problem before is that both of these are hydrogens that are being added, right? So that means that you have the possibility, if you draw out both of your structures here, it's possible that these are the same. And why are these the same? Right? It looks like we have this pair of enantiomers, but they're actually the same because this is a meso compound. So this is just something you got to be careful of. If I'm asking you to draw all the stereoisomers and you give me both this and this, you're going to get docked points because those are actually identical. So in terms of, again, you'll always see it as hydrogen gas, but there are four catalysts that you might see: platinum, palladium, or nickel. And then the weirdest one is this Wilkinson's catalyst. So you might see something like this where you have H2 and then Wilkinson's catalyst. They're all doing the same thing in terms of hydrogenation and also a syn addition. Okay. Oops. So in terms of reaction mechanism, there is not anything I expect you to know in terms of reaction mechanism for catalytic hydrogenation. Oops. In terms of regioselectivity, you don't have anything to worry about because hydrogen, the same thing is going to be added to both of those positions, right? So highly substituted, more highly substituted, less highly substituted doesn't come into play here because you're just adding the same thing to both sides. So no sort of regioselectivity concerns. The main thing here, the main pain in the butt here is the stereoselectivity. And that is because it is a syn addition And the last thing I'll say is because you're adding the same thing to both vinyl carbons, you're adding a hydrogen to both vinyl carbons, got to watch for meso. Okay.